When a sample is ionized, it results in a chaotic, high-speed cloud of charged molecules and fragments spraying into a vacuum chamber. To identify the original substance, we need to determine the exact mass of these fragments, but we cannot place individual molecules on a physical scale to weigh them directly. To sort them by their mass-to-charge ratio, or m/z, we have to manipulate them using vacuum physics and electromagnetic fields. Mass analysis is ultimately an act of translation. It is the process of converting unmeasurable mass into secondary physical properties that we can actually measure. This matrix outlines 4 specific architectures developed to solve the m/z sorting problem. The first separates ions by tracking linear velocity down a vacuum tube. The second and third sort continuously based entirely on trajectory stability. The final instrument determines mass by measuring orbital frequency. Moving from simple velocity tracking to complex frequency detection provides the ultra-high resolving power required in modern analytical chemistry. This diagram illustrates the operational principle of a time-of-flight analyzer. A single electrical pulse pushes a discrete packet of ions down a field-free drift tube. That initial pulse gives every ion the exact same kinetic energy. To satisfy the energy balance in this equation, the lighter ions must travel faster. They arrive at the detector first, allowing the instrument to separate them by time. The physical reality of the instrument introduces an engineering flaw. Because the starting packet has physical width, ions of the exact same mass-to-charge ratio enter the tube with slightly different initial kinetic energies. Over the length of the flight, they spread out, blurring the arrival times and causing peak broadening. This schematic shows the electrostatic solution to that energy spread, the reflectron. Instead of a straight tube, the flight path ends in an electrostatic mirror. Look at the flight paths here. Ions with a slightly higher kinetic energy penetrate deeper into the electrostatic mirror before being reversed. They are forced to take a slightly longer flight path, allowing the slower, lower energy ions to catch up, so they strike the detector at the exact same moment. In a time-of-flight system, high resolution is achieved by mathematically manipulating the flight path lengths to correct for those initial energy deficits. Instead of timing discrete packets over a fixed distance, we can shift to a method that sorts a continuous stream of ions as they move through space. This diagram shows a quadrupole mass filter. It consists of 4 parallel metal rods. Opposing rod pairs are electrically connected, operating with a specific combination of alternating radio frequency and direct current potentials. These voltages create a highly dynamic environment. As an ion travels down the axis, it gets caught in a rapidly oscillating push-pull electric field governed by the Mathieu equation. We can translate the Mathieu equation into a physical analogy, a rotating saddle. A ball placed on a static saddle will immediately roll off, but if you rotate the saddle at the precise required frequency, the ball is locked into the center. This creates trajectory stability. For a given ratio of electrical fields, only a very narrow window of m/z values can ride the saddle, maintaining a stable corkscrew trajectory all the way to the detector. For all other non-resonant ions, the field is out of phase. Their oscillation amplitude wildly increases until they crash into the metal rods and are annihilated. The quadrupole acts as a continuously tunable stability filter. It purposefully destroys the vast majority of ions entering the chamber to isolate and measure one specific mass.
Those same oscillating fields can be adapted from a 2D filter into a 3D holding pen, allowing for the accumulation and sequential release of ions. By taking the geometry of the 4 continuous rods and folding them into a central ring electrode capped by 2 end cap electrodes, engineers built the quadrupole ion trap. Unlike the continuous filter, the trap holds a massive, varied cloud of distinct m/z ions simultaneously, suspending them together in stable figure-8 orbits. To read the mass spectrum, the instrument applies an escalating voltage ramp to the ring electrode. As the voltage increases, it intentionally pushes the orbits of the trapped ions past their mathematical stability limit. They destabilize one mass unit at a time, ejecting sequentially through a hole in the end cap to reach the detector. The trap operates as an electromagnetic bucket that catches a chaotic mixture of masses at once, only to carefully spill its contents in perfect numerical order. All of the analyzers we have covered share one major limitation. To record the signal, they require physically crashing the sorted ions into an electron multiplier transducer. The measurement destroys the sample. The Orbitrap operates on a purely electrostatic structure. It traps ions between a roughly cylindrical split outer electrode and a solid central spindle. The ions are attracted to the central spindle. To avoid crashing into it, their inward attraction must be perfectly balanced by the centrifugal force of their orbit around the spindle. This diagram highlights the crucial physical metric. As the ion orbits, the specific shape of the electric field forces it to slide left and right along the spindle in an axial harmonic oscillation. The frequency of this axial oscillation is entirely independent of the ion's initial kinetic energy. The speed of that oscillation is dictated purely by the ion's mass-to-charge ratio. Because the outer electrode is split, the ions induce an alternating image current in the metal plates just by passing near them. The instrument never crashes the ions. It non-destructively records this electrical current. The raw current is a chaotic blend of overlapping frequencies. A mathematical operation called a Fourier transform decodes that complex time domain signal, separating the individual frequencies to build a perfectly resolved mass spectrum. Bypassing destructive physical collisions to instead listen to electrostatic frequencies is exactly what enables the Orbitrap's extreme, parts per million accuracy. We have isolated mass by tracking flight velocity, writing stability boundaries, and measuring orbital frequencies. This table compares the instruments. Ion traps offer robust performance for routine analysis. Time-of-flight systems provide unlimited mass range for analyzing massive biological proteins. And Orbitraps provide the highest absolute mass accuracy, resolving peaks differing by tiny fractions of a unit. The modern solution is hybridization. Manufacturers physically link different analyzers together, ensuring the weaknesses of one instrument are perfectly covered by the strengths of another. In a typical tandem workflow, a robust quadrupole isolates a specific target ion and fragments it. That fragment packet is then orthogonally accelerated into a time-of-flight or Orbitrap analyzer for ultra-high-resolution measurement. The cutting edge of analytical chemistry relies on engineering these physical principles to work in concert. By leveraging velocity, stability, and frequency together, scientists can map the precise molecular architecture of everything from volatile toxins to complex human proteins.